This is one of the Lewis dot structures of ozone. You can see that there's a double bond and there's also a single bond. You would think that if you study the bond lengths of ozone, you would observe a short bond distance between these two oxygens, given that you have a double bond, and a longer bond distance between these two oxygens, given that you have a single bond. But actually, when we study ozone, we observe only one bond length between the oxygen atoms. And the bond length is partway between what you would expect for having a double bond and a single bond. This is due to the fact that ozone has two important resonance structures. And these two resonance structures contribute to reality, where the double bond is not on the left side or the right side, but that second bond is actually shared equally around the molecule. We'll be predicting resonance structures and how to form them by the movement of electrons in a little bit. An important fact is that resonance structures, you don't have one at a certain moment and then another at another moment, but that reality is a mixture of the important resonance structures. You observe the double bond not on the left or the right, but at all times equally around the molecule in this case. So electrons are not actually shifting from one moment to the next around this molecule, but they exist more or less equally around this molecule in delocalized orbitals. Okay, so you'll need to draw out Lewis dot structures and sometimes be able to recognize whether those Lewis dot structures can have other reasonable resonance structures. You can predict this oftentimes by seeing that many compounds which have possible resonance structures have double bonds next to single bonds, and also they might also have lone pairs of electrons nearby as well. So you draw out this Lewis dot structure originally, say. You could predict the other resonance structure by taking a lone pair of electrons on one of the atoms and moving it in to form a new bond. And when you do that, it forces this bond to move out and become a lone pair of electrons. This is because this oxygen has 2, 4, 6, 8 valence electrons around it, and it cannot have more than that. So if these lone pair of electrons were to form a new bond here, these electrons would have to move out, because if they didn't, there would be 10 electrons around the oxygen, which is impossible for a period 2 element. So, excuse me, electrons move in, forming bond, another bond moves out, forming a lone pair of electrons. You can see the results here. We now have a lone pair of electrons here where there was none before, and we now have a second bond here where there was no second bond before. So if you had drawn this original Lewis dot structure, you could get this other resonance form of ozone by moving electrons in to form a bond. Now we have a double bond. And taking this double bond and turning 2 of the electrons into a lone pair of electrons. As we see, now we've lost a bond, and now we have a lone pair on the right side. Okay. Now, you'll not only need to draw out other resonance structures and decide whether there will be important ones, but you'll have to also decide whether certain resonance forms are more important than others, they're greater contributors to reality, or less important. And their importance is determined by how stable they are. The more stable a resonance form, the greater it contributes to the reality of the molecule. The greater its depiction and characteristics are actually observed in the actual molecule. So In order to know whether a resonance form is stable, you need to consider that the less formal charge there is, the more stable it will be. But also, if there has to be formal charge, the more stable resonance forms have negative charges on the more electronegative element and positive charge on the less electronegative element. So take a look at nitrate here. You've heard of nitrate before. This actually has to have this formal charge, a negative, a positive, and a negative. Now, considering that, let's draw some resonance structures and see if the others are more stable than this original one. So we have single bond and double bond suggesting that we could draw a resonance form. So lone pair of electrons moves in, form a bond, and then electrons in the bond move out to form a lone pair of electrons. So now we've got a double bond on the left here and an extra pair of electrons up top. And so are these equally stable? They are. We see that all of the atoms here have full octets, and we have an equal number of bonds around the molecule, which are actually the most important factors. But besides that, we have the same formal charges, a negative, a positive, and a negative, a negative, a positive, and a negative. And the negatives and positives are on the same things. Negative and negative on oxygens, positive on nitrogen. Ditto here. So being that these are equally stable, these are both equal contributors to reality. And then later we can draw another resonance form where the double bond doesn't exist on the left or the top, but it exists on the right of the molecule. And so actually we observe that all of these bond lengths between nitrogen and oxygen are equal, and breaking any one of these first bonds would require the same amount of energy, bond enthalpy. But take a look at this molecule. You can draw another resonance form. A lone pair of electrons moves in if you're trying to minimize or optimize formal charge, and the electrons in the bond move out to form a lone pair here. So now we have negative, well, a lone pair of electrons on the carbon, and we lost one of the lone pairs of electrons on the nitrogen. So which of these is more stable? Well, we have the same total number of bonds, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and all of the atoms have octets if they need them. So then we consider, do either of these have less formal charge than the other? Well, no, the same amount, a positive and a negative, a positive and a negative. So then we have to consider which of these is more stable, considering is the negative charge on the more electronegative element. On the left here, we have a negative charge on nitrogen, which is more electronegative than carbon. So on the right here, having a negative charge on a carbon, that's fairly unstable. So on the left, having a negative charge on the more electronegative nitrogen, this is the more stable resonance structure. It is a greater contributor to the reality that we observe. Okay. One more side note here. On the AP exam, you don't need to know exactly very much about sigma bonds or pi bonds. I'll tell you that sigma bonds are have electrons held more closely between the nuclei. Nuclei, sigma bonds are here, whereas pi bonds form from electrons being shared between p orbitals. So sigma bonds, they are harder to break than pi bonds because the electrons in a sigma bond are closer to the nucleus. So that's all you need to know, really, except for the fact that, most importantly for the AP, the first bond between two elements is sigma, and the second and the third bonds are pi bonds. So take a look at acetylene here. How many sigma and how many pi bonds do you have? Well, we have 3 sigma bonds. We have this first bond between hydrogen and carbon, this first bond between hydrogen and carbon, and the first bond between carbon and carbon. But we also have 2 pi bonds. The second and the third bond between carbon and carbon, those are pi bonds. So the first bond between any two atoms is sigma, and the second and third bonds are pi. Thanks for watching, guys.